Okay, so let's talk about a couple of more concepts which we use for measuring the variability, which are variance, standard deviation, and covariance. So let's talk about variation. So in the beginning, when we were discussing the formal definition of variability, we discussed the dispersion of a dataset. So using the mean, median, and mode, we studied the central tendency of our data. How much we're going to study the central tendency was calculated using those 3 M's, the mean, median, and mode. So after calculating the central location of our dataset, we need to understand the spread of our dataset, how much the data is spread out. So for that purpose, we use variance. So the mean, we can say that the variance is the measure of spread around the mean, how much the data is spread out around the mean value. The formula for variance is something like this. So what we're doing here, we are taking each value of the variable x and we're subtracting it from the mean value of all the data points in x, and we are dividing it by the number of data points minus 1. Oh, sorry, we're actually also taking the square of the subtraction between the x and the x values and their means. So the reason we're actually doing that is, imagine in a concept the xi value is 0 and the mean is 3. So 0 minus 3 would yield us the value of minus 3. So in order to remove the negative value, in order to modularize all the negative values, we apply the square function and we get all the values are in positive and none of them gets a negative value, which ultimately results in a subtraction rather than a summation. I hope you remember that this E represents summation. So we are subtracting each x value with its mean and we are summing all the values together, and then we're dividing it by n minus 1. So the question you should ask over here is that why are we subtracting it with minus 1? So let's talk about population and sample. The population, you can say, is the bigger or larger amount of data, and we take from that population a small set of data and we call it a sample. All statistical analysis is dealt with a sample and population. The reason for that is collecting the data of a population is highly impractical. If you want to, let's take for an example, if you want to study the exam grades of all the students studying in America, in all the high schools, you would have to collect infinitely large amounts of data and to apply concepts and statistical analysis on them, which would take you decades, even years and years of conducting surveys and collecting data and then validating that data. And then after even somehow you succeed in correctly gathering it, it will take you enormous amount of effort and the expensive computational resources you're going to spend on calculating the statistical analysis on that population data, which is highly impractical and no one does that. So what we do is we select a couple of states where you can say we collect data of high school students of a couple of states in America, and then we use it as a sample. And after that, we apply statistical analysis and we describe the data. And then after describing the data, we further explain it on the sample. And then we infer our learning and understanding from that sample and we apply it on the population. So inferential statistics, we will get a better understanding of how we can approximate our values of sample data and apply it to the population data. For now, you can say that population and sample, population is a big dataset which we do not use, and sample is a subset of that big dataset on which we apply all the statistical analysis. So we have already seen variance and we have seen the population and sample concept. So if we want to calculate the population variance and sample variance, we basically, like I said earlier, we mostly statisticians and data scientists mostly deal with sample data and approximate the parameters for the population data. By what I mean by parameters and approximation is, let's take for variance, we are going to calculate variance of the sample dataset and we're going to apply or approximate a value that is as close as possible to the population data. Do you remember my question? I asked you about the n minus 1. Why do we divide it by n minus 1? The reason for that is we make sure that the approximation we are doing of the sample variance to the population variance actually n minus 1 ensures that, because it ultimately enables the sample variance to get larger and it approximates better to the population variance. So let's think about this intuitively. The population variance, it's a lot of data, so the variance should be larger than the sample variance, right? So for that reason, if I calculate a sample variance, my next step would be the next intuitive understanding would be okay, the population variance should be larger than this sample variance. So the mathematicians and statisticians came up with this beautiful concept that instead of dividing it by n, we divide it by n minus 1, and it increases the variance to a certain value, and it compensates our lack of information about the population data. Standard deviation. This is the next concept, and it is nothing. It is the same as variance. The only difference is that we take a square root of the variance to get standard deviation. So why do we need standard deviation at all? It's just a square root. Why are we square rooting the variance to get an entirely different metric? What does this metric tell us? Is it even important? So for that fact, we need to understand that variance is often too large for visualization or comparison because of the squared value. We're squaring the subtraction between the values and their means, and whenever we're squaring them, and for the fact that we are actually dividing it by n minus 1, which adds to the increased value of the variance, it becomes difficult to visualize it and to compare it with other values as well. We needed a different metric for that. For that, we need the square root of variance gives us the value that can be used for comparison and visualization as well. This is, you can say that, a trick or something. Even it's not fair to call it a trick, but you can say it's smart. It's really smart to do that, to apply square root to the variance so that we can get a value that is easily compared and visualized with other sample data sets, with other values, and it is a metric that can be used more appropriately than variance. So the next concept we're going to discuss is the coefficient of variation. Whenever we divide the mean by standard deviation, we get the coefficient of variation. So the next question is, why do we need it? Why are we dividing the standard deviation by mean? We just square rooted the variance to get standard deviation. Now we're dividing it by mean. It's important that to do that, it ultimately gives us information about the dispersion of data that is relative to its mean. Now we have information for comparing two different data sets. Whenever we need to compare two data sets, the coefficient of variation can be used because we have different means for the both data sets, and we are going to use this value in relative to those different means to compare them. So here we have an example of, we call it an example of variance. So we have the mean of the data points, we calculate the mean, then we calculate the difference between the data point and the mean, and we have a column, the column number 3, which has the difference. As you can see, there are certain differences that are in negative. So the reason I mentioned before, the reason we have this squared, we have a square value, is to convert the negative into positive. So this is how we calculate the squared difference and the variance for the fact. And after, in the end, we divide it by 16, which is the total number of values minus 1, and we get the variance. So the coefficient of variation, as you know, as you saw before, that it gives us information relative to the mean. Imagine that you have two types of tests. One has the regular test and the other one is a different type of test. We calculate the mean and the standard deviation. And for that fact, we need to understand that both of these tests have different means. So in order to compare them in a much better way, we add another variable, which is the coefficient of variation. And the coefficient of variation divides the standard deviation by the mean and ultimately gives us these two values, and which is a better metric for comparison whenever we are comparing two data sets and two different sample sets. And so this is a very unique and smart way to do it.